What if I told you that everything we know about the universe might be wrong? For decades, physicists have tried to merge gravity with quantum mechanics, creating a theory of everything. But what if gravity isn't quantum? What if gravity is fundamentally different from the other forces of nature? New experiments are diving into this very question, and the answers could revolutionize our understanding of reality itself. Stick around as we explore the mind-bending possibilities and groundbreaking experiments that could reshape physics forever. Physicists have long sought to unify gravity with quantum mechanics, which describes the behavior of particles at the smallest scales. The problem is that gravity, as we understand it through Einstein's general relativity, works beautifully on a cosmic scale but breaks down when applied to the quantum world. This has led to the search for a theory of quantum gravity that could reconcile these two frameworks. The most popular candidates have been string theory and loop quantum gravity. But what if they're barking up the wrong tree? What if gravity is not meant to be quantized like electromagnetism or the strong and weak nuclear forces? The challenge lies in the fact that gravity is incredibly weak compared to the other forces. Think about it. A tiny magnet can lift a paperclip against the gravitational pull of the entire Earth. This disparity makes it difficult to test quantum gravity theories in a laboratory. To date, no experiment has been able to directly observe the quantum effects of gravity. It's almost as if gravity exists outside the quantum realm, making some physicists question whether gravity even belongs in the same category as the other forces. Could it be that gravity is a classical force that doesn't play by quantum rules? Recent experiments are attempting to answer this very question. For example, researchers are using ultra-cold atoms to create a Bose-Einstein condensate, a state of matter that exhibits quantum properties at macroscopic scales. By observing how these atoms respond to gravitational fields, scientists hope to catch a glimpse of gravity's quantum nature, if it exists. Another fascinating approach involves using laser interferometers, similar to those used to detect gravitational waves, but with a twist. These experiments aim to detect tiny deviations in space-time that could indicate a quantum behavior of gravity. If these experiments show that gravity is not quantum, the implications are staggering. It would mean that gravity is fundamentally different from the other forces, possibly arising from a deeper yet undiscovered layer of physics. It could even lead to a paradigm shift in how we understand space, time, and the very fabric of reality. Concepts like black holes and the Big Bang, which rely on a quantum description of gravity, would need to be re-examined. We might even discover that our universe is just one of many, each governed by its own rules. So where does this leave us? If gravity isn't quantum, we'll have to rethink much of what we know about the universe. But that's not necessarily a bad thing. Scientific progress often comes from questioning the status quo and exploring new ideas, no matter how radical they seem. The next few years will be crucial as more experiments come online, testing the boundaries of our understanding. Whether we find quantum gravity or something entirely unexpected, one thing is certain: physics is about to get a whole lot more interesting. Einstein's theory of general relativity has stood the test of time, accurately describing how gravity works on large scales, from planets to galaxies. However, Einstein himself struggled with the idea of unifying gravity with the then emerging field of quantum mechanics. He famously called quantum entanglements "Pookie action at a distance" and doubted that the universe operated on such probabilistic principles. If gravity isn't quantum, Einstein's hesitation might have been more than just a philosophical disagreement. It could suggest that gravity indeed follows a different set of rules, separate from the quantum world. One of the biggest mysteries in modern physics is the nature of dark matter and dark energy, which together make up about 95% of the universe. Could the answer to whether gravity is quantum be linked to these elusive substances? Some scientists speculate that if gravity isn't quantum, it might help explain why we can't directly detect dark matter. Perhaps dark matter interacts with gravity in a way that doesn't fit into our current quantum theories. Understanding this interaction could unlock new insights into both dark matter and the true nature of gravity. There's a mind-blowing theory called the holographic principle, which suggests that our entire universe might be a 3D projection of information encoded on a 2D surface. If gravity isn't quantum, this idea could take on a whole new meaning. It might mean that gravity is an emergent phenomenon, arising from this lower dimensional information rather than being a fundamental force like electromagnetism. If true, this could revolutionize our understanding of space and time and suggest that the universe is even stranger than we ever imagined. What if gravity isn't a fundamental force at all, but rather an emergent property of more basic interactions? Some theories suggest that gravity could arise from the entanglement of particles in quantum systems. This means gravity might not exist at the smallest scales, but only appear as a result of complex interactions. If this is the case, our quest for a quantum theory of gravity would be misguided. Instead, we'd need to rethink our approach, focusing on how gravity emerges from other physical processes. String theory and loop quantum gravity are two leading candidates for a theory of quantum gravity, but they're still incomplete. Both face significant challenges in making testable predictions, and neither has provided a definitive answer to the quantum gravity puzzle. If gravity turns out to be non-quantum, it could mean these theories are fundamentally flawed. This would be a major setback for decades of theoretical work, but it would also open the door to new ideas and possibly more fruitful lines of inquiry. One of the biggest hurdles in this field is the sheer difficulty of experiments. Proving that gravity is quantum requires detecting incredibly small effects that are far beyond our current technological capabilities. Even the most advanced experiments, like those using atom interferometry or space-based observatories, are only scratching the surface. If gravity doesn't show signs of being quantum in these experiments, it could mean we need to rethink how we even approach the problem. If gravity is truly non-quantum, this has profound implications for theoretical physics. It could mean that the universe is fundamentally classical at large scales, and quantum mechanics only applies to certain interactions. This would force a major revision of our theories of black holes, the Big Bang, and even the nature of space-time itself. It would also raise new questions, such as why gravity is so different from the other forces, and what this means for the ultimate structure of the universe. Einstein's theory of general relativity tells us that gravity affects time. The stronger the gravitational field, the slower time moves. But if gravity isn't quantum, could there be limits to this effect? If gravity is classical, the way it interacts with time could differ significantly from our current understanding. This could lead to new insights into the nature of time itself and how it flows in different parts of the universe, particularly in extreme environments like black holes or the early universe. Black holes are a key area where quantum mechanics and general relativity are expected to come together. But if gravity isn't quantum, our understanding of these cosmic objects could change dramatically. Concepts like Hawking radiation and the information paradox rely on a quantum description of gravity. Without it, we may need entirely new theories to describe what happens at a black hole's event horizon or what lies beyond. This could even impact our understanding of black hole formation and their role in galaxy evolution. If gravity isn't quantum, it could change our understanding of the early universe. The Big Bang theory suggests that the universe began as an incredibly hot, dense point where quantum effects of gravity would have been significant. But if gravity doesn't behave quantum mechanically, then this initial state might not be as we envision. It could mean that our models of the universe's birth and its subsequent evolution need to be revisited, possibly leading to new theories about the origins of everything. Quantum mechanics has radically altered our understanding of space and time, suggesting that they are not fundamental but emergent properties. If gravity is non-quantum, it could mean that space-time itself is more fundamental than we thought. This would have profound implications for our understanding of the universe's structure, possibly leading to a new theory that unites space, time, and gravity in a way that doesn't require quantum mechanics. Quantum mechanics allows particles to be entangled, meaning their properties are linked no matter the distance between them. Gravity, however, connects masses through space-time curvature. If gravity isn't quantum, it could mean that these two ways of connecting objects are fundamentally different. Understanding this distinction could help us learn more about the limits of quantum mechanics and how it fits into the broader picture of physics. Gravitational wave detectors like LIGO and Virgo have opened up a new window into the cosmos, detecting ripples in space-time from colliding black holes and neutron stars. But if gravity isn't quantum, what else could these instruments detect? Could they be picking up signals that we can't yet interpret because we're looking through the lens of quantum gravity? A non-quantum gravity theory might suggest new types of signals, such as those from exotic objects or unknown phenomena that these detectors could reveal. Most cosmological models rely on the assumption that gravity is quantum at the smallest scales. If this assumption is wrong, it could mean that our models of the universe's evolution are missing crucial information. For example, concepts like cosmic inflation and the nature of dark energy might need to be rethought. A non-quantum gravity could offer new explanations for these phenomena, potentially providing a more accurate picture of the universe's past and future. If gravity isn't quantum, it could support theories suggesting we live in a multiverse. Different universes could have different versions of gravity, some quantum, others not. This would mean that our universe is just one of many, each with its own set of physical laws. Such a discovery would have profound implications for our understanding of existence itself, challenging the idea that our universe's laws are universal. Quantum field theory successfully describes 3 of the 4 fundamental forces, but struggles with gravity. If gravity isn't quantum, it could mean that quantum field theory isn't the ultimate framework for all forces. This would be a huge shift in physics, requiring a new theory to describe how gravity fits into the larger picture, possibly leading to a deeper understanding of fields, forces, and particles. If gravity isn't quantum, it could lead to new technological innovations. For instance, it might help in developing more precise navigation systems or new forms of communication that exploit the classical nature of gravity. Understanding how gravity truly works could even open the door to new forms of energy or propulsion systems, potentially revolutionizing space travel and our ability to explore the cosmos. Some speculative theories suggest that consciousness itself might be linked to quantum processes in the brain. If gravity isn't quantum, it could challenge these ideas, suggesting that consciousness and gravity operate on fundamentally different principles. This could lead to new insights into the nature of the mind, possibly bridging the gap between physics and neuroscience in unexpected ways. Physicists have long sought a theory of everything that unifies all fundamental forces, but if gravity isn't quantum, this goal becomes much more complex. A non-quantum gravity would mean that any unified theory must accommodate fundamentally different types of forces. This could suggest that our universe is not as unified as we once thought, and that different regions or aspects of reality obey different rules. The advancements in experimental physics have become pivotal in addressing the question of whether gravity is quantum. Innovations like cold atom experiments and high-precision measurements are setting the stage for breakthroughs. These experiments can help bridge the gap between theoretical predictions and observable phenomena. By closely analyzing gravitational interactions at quantum scales, we may uncover the true nature of gravity and how it fits into the larger framework of physics. The debate surrounding the quantum nature of gravity is not just scientific, it's philosophical. Philosophers of science are deeply engaged in discussing the implications of different gravity theories. If gravity is non-quantum, it raises fundamental questions about the nature of reality, causality, and our understanding of the universe. This intersection invites a richer dialogue about what it means to know something in physics and the role of human perception in shaping scientific theories. Many alternative theories of gravity have emerged, especially in light of the difficulties in merging gravity with quantum mechanics. From modified Newtonian dynamics, MOND, to scalar tensor theories, these ideas offer different perspectives on gravitational behavior. If gravity is indeed non-quantum, These theories might provide insights that could guide future research. Exploring these alternatives can open new avenues for understanding gravitational phenomena and their implications. The Standard Model of Particle Physics successfully explains 3 of the 4 fundamental forces, but gravity has always been the odd one out. If gravity is non-quantum, this could necessitate a significant revision of the Standard Model. It may require incorporating new particles or forces to explain gravitational interactions, leading to a more comprehensive framework that addresses both the quantum and classical realms of physics. The exploration of whether gravity is quantum challenges the very boundaries of known physics. It pushes scientists to think outside traditional frameworks and consider untested hypotheses. By conducting experiments that probe the extremes of physics, such as those at the Large Hadron Collider or future gravitational wave detectors, researchers can test the limits of our current theories and uncover new truths about the universe. One speculative idea in quantum gravity theories is the concept of quantum foam, the notion that space-time is not smooth, but rather composed of tiny, fluctuating structures at the Planck scale. If gravity is non-quantum, this picture may change entirely. It could mean that space-time behaves differently under gravitational influence, leading to new insights about the fundamental nature of reality and the structure of the cosmos. Understanding whether gravity is quantum has significant implications for astrophysics. If gravity behaves differently than expected, it could alter our models of stellar formation, the dynamics of galaxies, and even the behavior of supermassive black holes. Astrophysicists must reconsider how they interpret observational data in light of these possibilities, leading to more accurate and nuanced models of the universe. If gravity isn't quantum, this could influence our approaches to space exploration. Technologies for propulsion, navigation, and even habitation on other planets may need to account for different gravitational interactions. New discoveries could lead to more efficient methods of traveling through space or understanding the effects of gravity on human health during long-duration missions. As researchers explore these profound questions, educating the public becomes increasingly important. Communicating the complexities of gravity, quantum mechanics, and their interplay can foster a broader understanding of science. This engagement can inspire future generations to pursue careers in physics and engineering, ultimately leading to more innovations in the field. The inquiry into gravity's nature exemplifies the need for interdisciplinary collaboration. Physicists, mathematicians, and even philosophers must work together to tackle the complex questions surrounding gravity and its relationship to quantum mechanics. This collaboration can generate fresh perspectives and innovative ideas that push the boundaries of what we currently understand. The quest to determine the nature of gravity is a long-term scientific endeavor. Researchers must remain committed to pursuing fundamental questions, even if immediate answers seem elusive. The pursuit of knowledge in this field not only enhances our understanding of the universe, but also drives technological advancements that can benefit society at large. This process fosters a culture of integrity and collaboration, ultimately leading to a deeper understanding of the fundamental nature of reality. To truly understand gravity's nature, bridging the gap between theoretical predictions and experimental results is crucial. Collaborative efforts between theorists and experimentalists can lead to innovative approaches that test the limits of current knowledge. By aligning theoretical insights with empirical data, scientists can refine their models and enhance our understanding of gravity. The double-slit experiment is a classic in quantum mechanics, demonstrating how particles can exhibit wave-like behavior. If we apply this to gravity, reinterpreting the results in the context of non-quantum gravity could provide unique insights. Could the interference patterns seen in light also apply to gravitational interactions? By conducting variations of this experiment with massive particles, researchers might uncover gravitational behaviors that challenge our current understanding. Atom interferometry has emerged as a powerful tool to test the principles of gravity at quantum scales. By using laser-cooled atoms to create interference patterns sensitive to gravitational forces, scientists can investigate the effects of gravity on quantum states. These experiments could yield crucial information on whether gravity behaves in a quantum manner or follows classical principles, providing insights into the fundamental nature of gravitational interactions. Researchers are now experimenting with measuring how gravity influences quantum states. By observing how particles behave in varying gravitational fields, scientists aim to determine whether quantum mechanics and gravity can coexist harmoniously. Such experiments could illuminate the conditions under which gravity influences quantum phenomena, further testing the boundaries of established theories. Quantum sensors represent a cutting-edge technology capable of measuring gravitational effects with extraordinary precision. These sensors can detect minute changes in gravitational fields, potentially revealing deviations that indicate whether gravity has quantum characteristics. As quantum sensing technology advances, it could play a pivotal role in exploring the quantum nature of gravity, possibly leading to groundbreaking discoveries. Space-based experiments offer unique opportunities to test gravity without the interference of Earth's environment. Missions like the European Space Agency's LISA Laser Interferometer Space Antenna are designed to detect gravitational waves and may provide insights into the nature of gravity itself. Observing gravitational interactions in microgravity could yield valuable data on whether gravity adheres to quantum principles or exhibits classical behaviors. Entangled quantum states challenge our understanding of information transfer and interaction at a distance. Researchers are investigating how gravitational forces influence entangled particles. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.